All right, peeps, we have a lot to do today. So, let's get action. Actually, it seems like it's been a while since we took a quiz. Probably getting close to quiz time. You don't think so? I don't know, let's think about that for a second. But while we think about that, let's continue our notes a little bit. We're ready for number 10, which says Solvy's and Kramer's rule. We did this yesterday. So who can remember, maybe by looking at your notes, who can remember our process if we're going to use Kramer's rule to solve this system? Now, let me just back up a second. Could we eliminate? Yep. Could we substitute? Yep. Could we use the inverse method? Yep, but who would unless you had to? We're going to do it with Kramer's rule. So here we go. Who remembers how this works? No, the derivative is something else. Yeah, we got all these D words. Derivatives are what we do in calculus class a lot. But we're going to find the determinant of the coefficients. Determinant of the coefficients. So there are my coefficients. Just like with elimination, they have to be lined up and now evaluated. Who remembers how to do that? We multiply, get 28, multiply, get -6, and then we subtract those. So the answer to the problem is 34. Now, what do I do with that 34? It becomes the denominator of my x and my y. Remember, when you solve a system using any method, your reason for doing that is to find where these two lines cross. That's going to be a point. Ideally, it will be a point. And x and y are fractions with 34 as the denominator. All right, how do I get the numerators? I build two more determinants by pasting the constants, that's these numbers over here with no variables, the constants, on top of whichever letter I'm solving for. So if I'm doing x, I'm going to cut those and paste them right on here. And if I'm doing y, I do the same thing, but I paste them here. Now notice, I am not rearranging anything. I am literally cutting and pasting. And everything stays right where it is. Nothing moves. All right, then evaluate these. So what's this one? 63 minus 2, is that 61? And this one's going to be -4 minus 27, so that one is -31. And there is, we talked a little bit about this yesterday, there is your absolutely hideous answer. That's a horrible answer. But it didn't bother me a bit because I didn't have to do anything with those numbers. It's not like substitution or elimination where you got to plug them back in, right? Beautiful. Done. Okay. Number 11, reflection matrices. Okay, so we talked about reflections before. Talked about symmetry, reflecting across the x-axis or y-axis or whatever. And there are matrices that will accomplish those reflections. And I want you to think about these matrices for a second. What do we call this one? What's this called? That's called the identity. And what does it mean to be an identity? It means if you times it by something, it stays the same, right? So multiplying by this would not change anything. I want you to think about what would happen if I made this negative. Well, let's look at it. Let's take a point like, we'll just take 1, 2. That's a point, 1, 2. And let's multiply it by this. Now, this is a 1 2. This is a 2 by 2, so I can multiply. And I'll come up with another 1 by 2. Let's see what I get. So I'm taking this row times this column. What does that equal? Row times column. 1 plus 0, which is 1. And then row times this column. 0 minus 2. So what did multiplying by this matrix turn the point 1 comma 2 into the point 1 comma negative 2? In other words, what did it do? It reflected it across the x-axis. Why did it reflect across the x-axis? Because it changed the sign on y. Remember, this is I, and this is j. Well, look what you did to j. You made it negative. That's making y negative. I is your x, j is your y, horizontal, vertical. You made it negative. Okay, so look at, and I know I've got them labeled there, but I really want you to think about this. What's that one going to do? That's going to reflect across y because it's changing the sign on x. And when you change the sign on x, you reflect across y. Okay? Now, what do you think this one's going to do? Well, that's going to change the sign on both of them, right? So think about that for a second. That's going to take your point, or your vector, if you want to think about it like that, 1 comma 2, and turn it into negative 1, negative 2. What does it reflect across? The origin. Hey, remember your test of symmetry? How did we test for symmetry about the origin? We changed the sign on both. Remember that? Takes you from quadrant 1 to quadrant 3, or quadrant 2 to quadrant 4. Okay, okay. And then what about this one? What's happening with this one? What did we do there? Well, this is supposed to be I, but now it's J. So if I switched the I and J, that's like switching the X and Y, which is a reflection across the identity. Y equals X. All right, so here we go. Consider this triangle. ABC with these vertices, and reflect it across the x-axis. So we are not going to do every one of these problems because they're all done the same way, but we'll reflect across the x-axis. So you have a choice. You can do it point by point, so I just erased it, but remember when I took that original point and I reflected it, you can do it like that with point A, point B, and point C. Or you can put all your points in a matrix. So this would be negative 1, 2, that's point A, 3, 0, and negative 3, negative 5. And then I'm going to multiply that by whatever I want to reflect, which in this case is x-axis. Now, the reason this will work is because what are the dimensions of this? 3 by 2, and this one is 2 by 2. So when I do my multiplication, I'm going to end up with another 3 by 2. Hey, hi. Okay, honey. All right. All right, so I have another 3 by 2. And when I get this 3 by 2, get all these numbers filled in here. What will that right there represent? That'll be the new point A, and this is the new point B, and this is the new point C. So here we go. Let's multiply. So remember how this works. row by column. That's going to give me this guy right here. So what's that going to be? It's going to be -1. And then row by column, that's going to be -2. 3, 0. -3. +5. Now, I know what you're thinking. You're thinking, Ms. Ford, I think I could do that without a matrix because I know what it means to reflect across the x-axis. But bear with me, in a minute we're going to be rotating like through, 119 degrees. So you're going to need to know how to do this multiplication, okay? So what are my new points? The original A, B, and C were here. That's what they gave me. And it looks like my new points, we usually call them A prime, B prime, and C prime. Those are the new points. And they are -1, -2, 3, 0. Wait a minute. How come that one didn't change? Because it's on the x-axis. And if it's already on the x-axis, it's not going to reflect anywhere, right? Across the x-axis. Okay, easy enough? Not hard. So if this was x-axis, we would do exactly the same thing for the y-axis. We would do exactly the same thing for whichever one you wanted to reflect across. Now, I got a little crazy, because down there at the bottom you'll see, what about y equals -x? I didn't give you that matrix. What would the reflection matrix for y equals -x look like? What do you think?
Would it be 0, -1?
0, -1?
-1, 0.
What do you think? I think that's perfect because she took the identity reflection and made it negative. Beautiful, beautiful, beautiful. Okay, so that's it. Now we're going to talk about rotating. So it would be like taking a triangle and then rotating it however many degrees you wanted to rotate it through. Okay, does that make sense? What we're doing? And the matrix that we're going to use to rotate, just in general, our general rotation matrix. What do I call it? I'll call it R sub theta for rotation. It's going to be cosine, sine, negative sine, cosine. Oops. I'm sorry, those of you over there probably moving. It's on the paper there, so you got it. That's going to be our general rotation. That's how we're going to rotate something. So, using the triangle in problem 11, which is the one we just did, so using these points, we are going to rotate through 118 degrees. So this is going to be cosine 118, sine 118, negative sine 118, and cosine 118. By the way, something really cool here, guys. What's the determinant of the rotation matrix? What's the determinant?
1.
It's 1. Yes. That's special. All right, here we go. So we're going to multiply these two together, and we can do that. You got a calculator, you're going to need it. We're going to find these numbers. So we're gonna take out our calculator, and we're gonna take this row times this column, right? So what are we gonna type in? First of all, make sure you're in degrees. So we're gonna take -1 times cosine 118. And then we're gonna add 2 times sine 118. I got 2.235. I'll just round off to the nearest thousand. Is that what you got? Somebody like nod or shake or something. Okay. So again, what we're doing is regular multiplication. We're taking -1 times cosine and adding 2 times sine. Alright, so what are we gonna do for this blank? We're gonna use that row and this column now. So we'll take -1 times, watch it, there's a negative there. -1 times negative sine plus 2 times cosine. So what's that one? Did you get -0.056?
Yeah.
Okay, now, what does that mean? Let's just stop right here and talk about what that means. That means if you took the point -1, 2, and you rotated it 118 degrees, it would end up at the point 2.235, just barely underneath, so it would end up down here. If you rotated that 118 degrees. All right, now take 30 and rotate it. So now you're taking this row times this column. So that one would be over here somewhere. Now remember, that original point started here. Does it make sense that if you rotated it 118 degrees, it would be right down here? Yeah, because that would be 90. You're going to slightly more than that. All right, and then do the last point. I want you to look at the sad expression on his face. He doesn't have math today. So
Yeah.
he's just totally
I miss
depressed
you.
about that. Now I just lost track of what I was doing. All right, I think I got -3.006. And what'd you get for that last one? 4.996? Now, change the angle, doesn't matter. You do it exactly the same way, right? Easy. Another observation though that I want you to make when you're ready. Everybody good with these? I don't know, I could have typed something wrong. So, let's look at just the original point, -1, 2. And that point, I'm going to think of it as a vector. The point -1, 2 would look like that. Now, what is the magnitude, if this is the vector -1, 2, What is its magnitude? Root 5. Now, when I rotate that vector, the magnitude shouldn't change, should it? So let's look at what its new version is. This was its new version. What is the magnitude of that vector? Remember, you square this, add them up, and take the square root. Now we'll have a little round off there, but it better be close to root 5. 2.235 squared plus 0.056 squared. Square root that. I get 2.2357. So this one has a magnitude of 2.2357. And the square root of 5 is 2.236. So rotating preserves magnitude. How about reflecting? I didn't check it with any of them, but when I reflected, shouldn't the magnitude stay the same also? Yep, absolutely. Okay, perfect. All right. So we don't need to do B because B is exactly the same thing. The difference with B is instead of having 3, we only have 1. We only do 1 point. All right, so now we're on to 13. Egg production. All right, so we got these eggs. The number of dozens of type I eggs sold to grocery store J is represented by A sub ij. All right, so let's look at this and figure out what's going on. All right. So what do these numbers mean? Tess, was your hand up a while ago? I thought I saw it. No? The problem tells you, what do these rows represent? The rows represent the type of eggs. So this matrix is a type of egg by, so the rows are type of eggs. And what do the columns represent? What are the J's? This is the dozens type of eggs, sorry. And then the rows are what? Grocery store, or columns are grocery stores? So this 100 right here represents 100 dozen large eggs sold to grocery store, whatever. This means 60 dozen large eggs were sold to, if this is Kroger, this is Meyer. So 120 is 120 jumbo dozens sold to Meyer. Got it? Okay. The per dozen price they charge for eggs is this. This is A or B. So what does this row represent? Well, okay, but the price of what? Per dozen of what? Yeah, so these are large eggs, and these are extra large, and these are jumbos. So the rows, again, represent the type of egg. And the column represents the cost or the price. Find the product B transpose A. Okay, what does transpose mean? Reverse the rows and columns. So B transpose would look like this. And then we're timesing that by A. dimensions of B transpose? 1 by 3. Remember guys, it's always rows first. Rows, 1 row. Columns are separate. So 1 by 3, and then this is 3 by 2. So our product is going to be a 1 by 2, right? So 1 row with 2 numbers in it. So we're going to take this column, or excuse me, this row times this column. So first times first, second times second, third times third, add them up. Please double check me, I got 382. And then do the second, same thing for the second column. $227.50. Now, to help you hopefully kind of see what in the heck is going on here, when I defined my matrices originally, I didn't put down, this is a 3 by 2. I said its rows are the type of egg and the columns are the store. And then the same thing over here. Now, when I did B transpose then, what did this matrix become? This became cost by type. And then I multiplied that by my original, which was type by store. See what's happening, guys? When I multiply, what has to match? The middle dimensions. And in these word problems, they have to represent the same thing. Not only do they have to be the same number, but they have to represent the same thing. So what do I end up with then? I end up with a matrix that gives me the cost by store. So Kroger spends $3.82 and Meyer spends this. See how that works? It is so cool. Okay, all right, one more. Oh, we already did that. What does this matrix represent? How much each store spends on eggs. All right, one more. And then I think we'll pause and do a bit of review because I really do feel like we need a quiz. I don't know why I feel that way, but I just feel that way. All right, so here we go. See if we can get through this problem. A building contractor has agreed to build 6 ranch-style houses, 7 Cape Cod, 14 colonial-style houses. The number of units of raw materials are shown in the matrix. So I have this matrix called R. And it's 576. Alright, so let's make sure everybody's clear on what this means. This is steel, wood, glass, paint, labor. And this is ranch, Cape Cod, and colonial. So what do the rows of this matrix represent? The type of house. And what do the columns represent? The material, right? Whether it's wood or paint or whatever. So let's look at this 8 right here. What does that 8 stand for? We need 8 units of glass for every colonial house we build. You understand what all that stands for then? Okay. Write a matrix product that gives the number of units of each raw material needed to build the house. Or build the houses. Alright, so what do you think?
We multiply it by like, what if we multiply it so it's by,
Material like oxygen.
no, 6, 7, 14.
Okay, so we have another matrix, 6, 7, 14. We haven't written it yet. I'll call it S. And what does that represent? Where did the 6 and 7, and 14 come from?
The number of houses.
Those are the numbers of each kind of house. So this 6 right here represents the number of ranch homes, and 7 Cape Cods, and 14 colonials, is that right? So the rows represent the number of houses, and the columns represent the type of houses. This is the number of colonials, number of whatever, ranches and everything. Okay? Now, she says she wants to multiply these. Can we just straight up multiply S times R? I think we can. Because, first of all, what are the dimensions of S? So 1 by 3. What are the dimensions of R? 3 by 5. Can they be multiplied? Now, you can't do RS, but can you do SR? Yeah, it says build a matrix product. So I'm going to build the matrix product SR. So I'm going to take, actually, I don't want to rewrite that whole thing. Is it okay if I just stick it over here? 6, 7, 14. Now, when you do that, when you multiply this 1 by 3 times a 3 by 5, you're going to end up with a 1 by 5. Everybody in agreement? And what will that 1 by 5 stand for? Well, you're multiplying houses times number. You're multiplying number by type, and then type by material. So we're going to end up with the number of materials. And is that what we want? Yeah. Find the number of units of raw materials. So this is going to give us the number of materials. That grammar isn't very good, but you know what I mean. All right, so here we go. So we're going to take row times column. And this is how much steel we're going to need. So 6 times 5, 7 times 7, and 14 times 6. I got 163. Did you?
Yes.
So again, make sure you know what that means. That means to build the houses I'm going to build, I need 163 units of steel. Okay? Now we'll do the next one, and the next one, and the next one. So now we're going to do column by column. He's sad too, he didn't have math today either. Right, Jude?
Yeah, I'm sad I missed yesterday too.
Oh, that's right, you were absent yesterday.
Alright, math on, y'all.
That's how I spend my days. I hope I'm not messing up. Am I matching any of your numbers here? I used to be able to multitask when you're 64, that just doesn't happen anymore. You okay with that? All right, take a minute and see if you can figure out B. Write a matrix product that gives the cost of each house. So we haven't used it yet, but in the problem, there are other numbers. Do you see that steel costs this much, wood this much, grass, see those? All right, see if you can write a matrix product for that. Okay? Take a second and do that for me.
These numbers.
Okay, well, we know the, so this is number, this is it must be typed by number, typed by cost.
Okay. Are you figuring it out?
So it's gonna be 0.
Wait.
I'm doing it typed by cost, which is
It's 1 by 5 alphabet, that's what.
Is it comes from the material?
okay, that'll be a try.
That'll make sense.
And then, what's one times the outside?
The last one has to be. Can you just make a vertical?
I just had it typed by cost so that I can multiply it by this.
We do.
So that's
Yeah,
the
it has to
way
be
I
material.
Then you would get the number, this is the number of costs, this is the number of material. This is a each guy.
Doing your
So this is the number of materials by the cost.
What is this?
Oh, wait. I'm not trying to do this. I'm trying to cost the house.
All right, any thoughts? What, George?
Since the cost matrix is 1 by 5, maybe we can reorganize the 3 by 5 material matrix into a 5 by 3s, which are equal. That should be
Okay. You know what, George? I kind of like that idea, but what if instead of writing your cost, what did you say your cost matrix was a 1 by 5? Could I write my cost matrix as a 5 by 1? So instead of writing it as a, what we call a row matrix, I could write it as a column matrix. So what, I like what George is thinking. George says, take this guy right here, which is type by material, and then multiply, which is a 3 by 5, and then multiply that by a 5 by 1 that represents material by cost. And that will give me a type of house by cost matrix. Do you see what I'm saying? So again, I don't want to rewrite that. So I'm going to take this matrix right here, and I am going to multiply it by this one.
Something. We're supposed to have about 3 by 5.
Okay, well, you're trying to find.
George, does that look like what you wanted to do? Now, you guys, listen. When I multiply these two together, this is my original matrix that they gave me. When I multiply it times this one, I am going to take this row times this column, and that is going to give me one number. And what is that number going to represent? The cost of a ranch house. Because I am going to take this times 1,600, this times 900, this, and add them all up. and that's gonna give me the cost of building a ranch house. Tess?
Wouldn't you type by
Yes, that's gonna be your answer, type by cost. Type of house, cost. So this represents a ranch house. These are the types of houses, and these are the costs of each one. So this is gonna be a ranch house cost, this is gonna be whatever the other one was, and this is gonna be whatever the other one was. Okay?
Wouldn't it be a 3x1?
Yes, the answer's gonna be a 3, oh wait, yeah, I'm sorry. It's a 3x1, not a 1x3. So it's the same idea, but it's gonna look like this. Yeah, is that what you were asking, Tess?
Is it?
I'm sorry, yes, it's gonna be a 3x1. The numbers are gonna be the same, I just have it written wrong. Yeah.
So if we just, like, if we flipped the other matrix and we just had a 1x3 written out, would that be wrong or no? Because we'd still be getting the same answer.
No, that would be okay.
So if
Yeah.
we just have it written.
Yes,
then-
yes.
Okay.
And then you would have to multiply it at the beginning.
Yeah, yeah.
So, let's go ahead and figure one of those numbers so we get it right, so we can talk about it. So, row by column. So 5 times 1600, 22 times 900, 14 times 500, 7 times 100, and 17 times 1,000. So I think a ranch house costs this much money. And then doing the same thing with this row and the same thing with this row would give you the cost of the other two homes. So we end up with the type of house and the cost of each one. Ranch, whatever CC stands for, and CG. Is that okay? All right, 7-2 homework will be due on Thursday. Let's do a quick review. I think the quiz we take next time is only gonna be a really, really short one, but I wanna make sure we've covered a lot of new ideas, and I wanna make sure that you haven't, that you've taken time to process it, okay? So let me put a couple matrices up here. Okay. Anything's fair game in 7-1 and 7-2. So let's take a minute. Hopefully, maybe before we take the quiz, remind me of this, I'll turn back the 7-1 homework because there were some issues with that. We probably want to talk about those before we take the quiz. But let's do a couple quick review problems here. What if I said this? I heard somebody say, can't do that. Can't do that. What's wrong? They're not the same size. If you could do it, if they were the same size, you just add corresponding entries, right? But since they're not the same size, you can't do that. How about this? Can I do this? What are the dimensions of A? What are the dimensions of B? Can I do this? Nope. But can I do B times A? And we just did some multiplication. Are you okay with that? Good with multiplying. All right, what if I said this? We take those numbers right there, and then what?
Add the first two.
Take the first columns and paste them here exactly. And then we multiply, 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 add them all up, get a number. Then multiply, 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 add them all up, get a number. How did lunchtime go today, Ayrton?
It was good.
You just sign a bunch up?
Yeah.
Good. So, we multiplied all these and added them up, we multiplied all those and added them up, and then what do we do with those two numbers? Subtract them. And we always start here. Remember, that is the first multiplication. So it's these minus these. Remember that? Okay. What if I said this? We talked about this today too. What does that mean? That's the transpose of B. And the transpose of B would have row 1 is now column 1. Right? What if I said this? What does that mean? I think we talked about it. Let me check my notes real quick to see if it's in the vocab. Yep, it's in the vocab. I know we talked about it. It means the trace of A. And the trace of A simply means we add up the numbers on that diagonal. We add them up. So the trace of that would be 4. There is no trace for B, because in order to have a trace, you have to be squared. Okay? No determinant unless you're square. No trace unless you're square. Now, what if I said, here's matrix C. And I said this. What am I doing there? Finding the inverse. How do we do that? First we find the determinant. And what would my determinant be? 8. If you said 8, you're right. If you said something else, you're not. It's 5 minus negative 3. That's the determinant. Then what? Well, now wait. I don't just start dividing. What do I have to do first? I have to make a new matrix by switching these and changing these signs, and then I divide by 8. So that actually would be the inverse. Sometimes you simplify, but he doesn't, so that would be the inverse. Right? Okay. Let's see. What else? What if I said to you, what is the reflection matrix for the y-axis? Don't look at your notes. See if you can figure this out. Do not use brain space to memorize all these. Don't think about it.
Is it 1, 0,
It's going to start with this, right? And if you're reflecting across the y-axis, what are you doing? Changing the sign on x, right? If you're going across the y-axis, and if you want to change the sign on x, then these are the x's right here. That's I. So would that be your matrix? Right? This is going to be a no calculator quiz. So what if I said, what is the rotation matrix for 60 degrees? Oh man. Oh man. Okay. So first of all, we got to remember that it's cosine, sine, and I know we just talked about this today, but you got till Thursday to get it memorized. It's easy. Cosine, sine, negative sine, cosine. Okay? Now you got to figure out the cosine and sine of 60. Okay? Those aren't going away just because we're past trigonometry. So here we go. 60 degrees. This would be a √3, a 1, and a 2. Would you agree with that? So my matrix is going to be cosine 60, which is 1/2, 60, which is root 3 over 2 negative root 3 over 2. Now, with no calculator, I can't ask you to do any rotation matrix, but I can do 60s, right? And 45s, 30s, 120s, things in other quadrants. I won't, oh gosh, that's such a cool problem. I won't, make a note. I'm sorry, please, but I got it. All right, so what else? Let's see, what else?
You get a reference sheet at all?
No! No, we're way past that. Oh, one more thing to remember. There might be, just because I love it, there might be a Kramer's rule problem. So we practiced one last time, we practiced one today. Review Kramer's rule, make sure you understand how that works. Okay? All right. That's a great paper, so I'm gonna write it this.